Suppose that there are two different trucks moving with an equal amount of kinetic energy. If one truck is lighter than the other truck, in the sense that that one has less mass, which truck has more momentum, the lighter or the heavier truck? So again, we got two trucks, right? One is smaller, the other one's bigger. They have the same amount of kinetic energy. Maybe it's obvious that in order for the two trucks to have the same amount of kinetic energy, the one that has less mass is going to have to be moving faster, right? To kind of counterbalance that lower amount of mass in such a way, again, that the kinetic energy, right, which kinetic energy is given by the formula 1/2 mv squared, right? This is what we've said. I'll just put Ke here for kinetic energy. So if I want to have the same amount for each truck, but one again has less m, the other one's going to have more v to counter that. It's kind of what I'm saying. But if we look at momentum, and I'll just worry about magnitude here and write p is equal to mv, wouldn't it kind of work the same that since the lighter truck is going to have more velocity, would that mean they'd have to have the same momentum too? Well, no, right? Because these formulas are different. This one is 1/2 mv squared. And one way of looking at this is to say for kinetic energy, which is, if you ask, we said momentum is a measure of motion, right? But isn't kinetic energy kind of also a measure of motion? It is. In the language of energy, you could argue that kinetic energy is a measure of motion. It measures it differently, though, because kinetic energy, for one thing, doesn't include direction. It only tells you how much. And that makes sense because energy really isn't a direction-containing type of quantity, right? It's not supposed to convey that type of information. Energy was also based on how much work it takes to make something happen. So in that sense, the kinetic energy formula literally comes from how much work did it take to get this object moving at the speed. And, what we're looking at for these two trucks is you could say the engine of the two trucks, respectively, had to do the same amount of work, disregarding any losses due to drag and friction and stuff like that, to get each truck moving in the way that they are moving now, such that the light truck is moving faster than the heavier truck. But I don't know if any of that has given me any insight yet as to which one has more momentum. One way of looking at it, though, is to recognize that in kinetic energy, the speed or the magnitude of velocity is more impactful towards how much kinetic energy. So if you think about I'm going to lower the mass but increase the speed, right? So going from maybe the heavy truck to the light truck, but I want to keep kinetic energy constant. I'd have to not increase the speed all too much because since it gets squared, if I increase it a lot, if I took mass down to half and doubled velocity, doubling squared is 4 times, right? So that's a huge impact. So that means we can't raise the velocity too much, but mass and velocity kind of have equal impact on the amount of momentum. So that means I think that when the lighter truck, if you say, hey, I went from the heavier truck to the lighter truck, I reduced the mass, increased the speed, but I didn't increase the speed that much. That means the lighter truck must have less momentum and the heavier truck therefore must have more momentum. Now, if you didn't follow all that, here's a simple trick I want to share with everybody for doing this. I'm going to kind of make a little table here. And what I'm going to do, I think, is, let's see, I'm going to put mass here. I'm going to put velocity here. And then, maybe I'll put kinetic energy here. I was going to put in the whole formula, and I realized I'm probably going to run out of space. And I'll put momentum right here, just multiplying mass and velocity. And I'm just going to say, okay, let's say that, let me start with the heavy truck, I guess. Let's say that the heavy truck has a mass of 2 and a velocity of 1. You might say, well, why did I pick those numbers? Well, they're really simple numbers, right? Actually, I suddenly realized maybe I wanted to pick even simpler numbers, but I think this will work. I mean, this doesn't have to be perfect, right? But if I think about, okay, so what's the kinetic energy for that? It's going to be 1, right? What's the momentum for that? It's going to be 2. But now to get to just an example of a light truck, I'm just going to divide the mass by 2 and say, okay, there it is. It is now 1. What should the velocity be? Should the velocity then just go up to 2 to counter that? Well, if I made the velocity 2, I'd have 1/2 times 1 times 2 squared, which would actually be kinetic energy of 2, which wouldn't work because we said they have an equal amount of kinetic energy. So the way to achieve that is to put in the square root of 2 here. Because if I take, in that sense, for kinetic energy, I would do like 1/2. I'll actually put in like the numbers going into the formula here. 1/2 times 1 times, and then it would be like that root 2, but that would be squared, right? Which, so that's, I think that's equal to 1, right? Because it's 1/2 of 1, but root 2 squared is just 2, so that's like half of 2, which is back to 1, right? But what is the momentum going to be? It's going to be the square root of 2. Square root of 2 is smaller than 2, so that means the bigger one is clearly this heavier truck right there. So I'll just draw an arrow right there to identify my answer. And, you know, there are different numbers. Like, you could choose whatever numbers you think are simple to work with. I mean, maybe you didn't like the square root of 2 thing. Like, how would you fix that? Well, maybe if I'd made this a 4 and then went down to 1, and then this one would go to 2. Those are maybe easier to look at numbers. And you can kind of play around with it and guess what numbers work. But this is a cool thing in case, like, just looking at formulas and you're like, okay, how do I answer this with a formula? That can sometimes be hard. But what's cool, though, is that whatever numbers you choose here, as long as you make it so the kinetic energy satisfies the condition of it being the same for both, the answer will work no matter what numbers you had here. So even if, like, if, say, the heavier truck was only 5% heavier than the light truck, the answer would still be the same. The heavier truck, provided their kinetic energy was the same, the heavier truck would definitely have the larger momentum.